In this video, I want to talk about Ortho Para Meta Addition via electrophilic addition, electrophilic aromatic substitution. Okay, essentially we were doing Friedel-Crafts acylation, alkylation, all that good stuff. Okay, now we need to define what are electron donors. Okay, electron donors. Okay, and usually these are O minuses, OH, NH2, NR2, right, which is just some sort of R group with two R on it. We have OR, usually see SH, which is a thiol group. So these are all the electron donors. Alkyl halides also, yeah, so arrow. I'm just going to say arrow. Okay, so these are electron donors. And what these are, electron donors or ortho para directors. Okay, so we need to know that anytime we have an electron donor on the ring, we get the ortho and the para product. We get a mixture. Now with electron acceptors, these are meta directors. Okay. Now what are electron acceptance? You'll see NO2. You'll see SO3H. You'll also see carboxylic acids. You'll see nitrile groups. You'll see aldehydes. You'll see COR. Okay, so these are all the electron donors, and we could go on and on. Okay, now you might be saying to yourself, hell no, I'm not gonna remember this. Well, you don't have to, and I'm gonna give you a trick to this. Anytime you have double bonds, anytime you have some sort of double bond, triple bond, those are electron acceptors, which means that they want to participate in resonance. So don't even remember all this stuff. I wanted to throw that out there. Anytime you have double bonds, we're going to get the meta product. It's going to be a meta director. Anytime you do not have any double bonds at all, or anything, any double bonds or any triple bonds, they're electron donors. So that being said, let's get started. Okay. What if I have this molecule here? Yeah, and I decided to add acetyl chloride and aluminum trichloride. What would we get? Well, again, I see no double bonds, okay? Which means that this has to be an electron donor. But what do we say about electron donor? We'll get a mixture. So I'm gonna get this product. Okay, we get the ortho product plus the para product. Get a mixture. Okay, now this is the predominant. Okay, so this is predominant. This is the major product. Okay, so this is typically, because it's simple, more stable. It's, you notice that the groups are just too close to each other. So the para product is usually what you'll get. Okay, now what if I have this molecule here? Okay, this is nitrobenzene, and we decided to add CH3Cl and aluminum trichloride. What will happen? Well, again, NO2 looks something like this. Is nitrogen that has a double bond oxygen to a single bond in oxygen and negative charge. Okay, that's how the molecule looks. I see double bonds there, so this has to be a meta director. So therefore, the product that I'm going to get is something that looks like this. Okay, I get the CH3 in the meta direction, and now this is nitrotoluene. Okay, so that would be the product that I would get. Now, what about this? What if I take a carboxylic acid and I add this molecule here and iron trichloride? What would I get? Well, again, I see double bonds here, so I'm thinking this has to be an electron acceptor. So it's electron acceptor, electron withdrawing group. So therefore, I'm going to get meta orientation. So therefore, the product for this synthesis would look something like this. Okay, so that would be the product that I would get. Now, what about this one? What if I took toluene? Okay, what if I took toluene? Okay, and I added this molecule. Okay, and iron trichloride. What would I get? What would be the product? Well, you see that again, this is Friedel-Crafts acylation. Okay, we're taking an acid chloride and adding on to the benzene ring. Well, remember, this is a CH3. I see no double bonds here, so this is an ortho para directed. Okay, I see no double bonds there. It's not an electron acceptor, so it's an ortho para directed. So therefore, I'm going to get a mixture of products. So in doing that, I'm going to get this. I have my CH3, and this is now bonded to my ketone. And for simplistic reason, I'm just going to put pH, which simplify the phenyl group here. Okay, so I'm getting a mixture of that plus the para product. Okay, so that would be the product that I would get. Okay, these are the products that I would get. I would get a mixture. Now, which one your professor might want, it'd probably be this. It's the para product. It's simple, more stable. Simple, more stable. The electron groups are far away from each other as possible. Now, what if I take benzene? Well, not benzene, but what if I take this molecule here? Okay, SO3CH, and I added Cl2ACl3. What would I get? Well, again, benzene sulfonic acid, and you should know these by now in the structures. It's an electron accepting group. It has double bonds. It has double bonds. So I'm only going to get the meta product. So I'm going to get chlorine in the meta position. Okay. What else do I have? Again, if I take an alcohol, right? So if I take phenol, okay, so if I take phenol and I add Cl2 and aluminum trichloride, what will I get? Well, again, I see no double bonds again. Okay, so this has to be an electron donor, which means I'm getting ortho para products. I'm getting chlorine in the ortho position. I'm gonna get chlorine in the para position. Okay, so here's the big takeaway. If no double bonds is not on your ring, that means that's an electron donor. It wants to give away electrons, right? It's electron donor, so you're gonna get ortho para product. If we see double bonds, that means it's a meta director. It wants to participate in resonance, and so actually, and that's how I usually think of it. And so actually, we're gonna get meta orientation. Okay, so all these throughout is very important to memorize and know, but at the same time, if you know the logic that anytime I see a double bond, I'm going to get meta orientation. And anytime I do not see one, I'm getting ortho para direction, then this all of a sudden, we don't have to memorize this anymore.